So this turns out to be 5 by 36. I call this equation 1. 486 nanometer. See, empty number of problems being repeated from the same concept. First line of the Lyman series is 1125 angstrom. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram, Pre-University, Mysuru. In this session, we will continue our discussion on the problems part from the chapter Atoms. Hope you have visited the previous session, thoroughly worked out the problems, and have come prepared for my today's class. The first problem. Now, the first problem says the first member of Balmer series. The given series is Balmer series of hydrogen atom has a wavelength of 656.3 nanometer. First member of which series? Balmer series. It is having a wavelength of 656.3 nanometer. I have to calculate the wavelength and frequency of second member of the same series. I have to calculate the wavelength and frequency of the second member of the same series, which means the same Balmer series. So given is the wavelength of first member of the Balmer series. So therefore, as we did, we will note down the solution. Now, first member of Balmer series. So as I told, the solution here lies identifying the principal values, the N1 and N2 values of the given series. And again, as I told, the N1 value is always fixed for a given series. So this is Balmer series. So N1 is 2. And it is the first member of Balmer series, which means N2 is equal to 3. Now the same empirical formula 1 by lambda is R 1 by N1 square minus 1 by N2 square. And as I have told, never substitute without writing the formula. Now on substitution, 653 nanometer is given, minus 9 nano. And when I have told where there is comparison of two expressions, do not substitute for R as it gets cancelled. So this is R 1 by N1 square, 2 square is 4, minus 1 by 3 square is 9, or on simplification, 653 minus 9 R. So this turns out to be 5 by 36. I call this equation 1. So equation 1 with respect to first line of Balmer series. But I have been asked to calculate the wavelength of second member of Balmer series. So, for second member now, second member of the same series ಅಂತ ಹೇಳಿದ್ದಾರೆ, which means second member of the Balmer series. N1 remains the same. It is Balmer series only, alva. I told N1 value is fixed. Second member ಆಗಿರೋದ್ರಿಂದ N2 is 4. Again, now use the same formula. 1 by lambda is R. 1 by 2 square, which is 4. This is equation 2. So, I have framed equation 2 for second member of Balmer series. Now, equation 1 divided by equation 2, lambda for the second member turns out to be 486 nanometer. So the wavelength of the second member of the Balmer series is 486 nanometer. Is the problem complete? No. I have also been asked to calculate the frequency of the second member. So we know frequency nu is C by lambda 2. C is 3 into 10 power 8. Lambda 2, 486 into 10 power minus 9, which is nearly 6 into 10 power 14 hertz. See, I've bisected the problem analytically. Take down a calculator, check for the simplifications. You will become thorough with the calculations. Next one, students. The same way, see, umpty number of problems being repeated from the same concept. Second one, the first member of Balmer series of hydrogen spectrum has wavelength 6563 angstrom. Matpuna, it is the first member of Balmer series. It is in the visible part of the spectrum. So many problems related to it. First member of Balmer series of hydrogen spectrum has wavelength 6563 angstrom. Compute the longest wavelength. ಏನಿದು ಲಾಂಗೆಸ್ಟ್ ವೇವ್ಲೆಂತ್ ಅಂದ್ರೆ ಪ್ರೀವಿಯಸ್ ಸೆಷನ್ ಅಲ್ಲಿ ಮಾಡಿದ್ವಿ. ಲಾಂಗೆಸ್ಟ್ ವೇವ್ಲೆಂತ್ is the wavelength of the first line of the series. The wavelength of the first line of the series is called longest wavelength, and series limit andre it is nothing but the shortest wavelength, which is the wavelength of the last line of Lyman series. So given the wavelength of first member of Balmer series, I have to calculate the wavelength of the first line and the last line, which is also called series limit of Lyman series. Now, what is given, students? Wavelength of first line again. So, for first line of Balmer series, for first line of Balmer series, again N1 is 2, N2 is 3. As usual, first line of Balmer series, N1 is 2, N2 is 3, which means again 1 by lambda is R, 1 by N1 square, N2 square. The same empirical formula, just changing up with N1 and N2. Now, so now he says in angstrom, 6563 into 10 power minus 10. This is R, 1 by 4 minus 1 by 9. Again the same thing. History keeps on repeating with these calculations into 10 power minus 10. Again, this is 5 by 36. If you have gone through all my sessions, if you are thorough with framing up until equation 1, 2 marks very evidently without any difficulty in your bags. Now, the first part of the question is to calculate the wavelength of the first line of Lyman series. Longest line, but for Lyman series now. So, for first line of Lyman series given Balmer, I am calculating the wavelength of first line of Lyman series. So for first line of Lyman series, N1 is 1, N2 is 2. Again, lambda has to be calculated in this case. So 1 by lambda is R, 1 minus 1 by 4. 1 by lambda is R, 3 by 4. Equation 2. Again I have equation 1. Again I have equation 2. What will I do, students? Equation 1 divided by equation 2. Lambda turns out to be 1125 angstroms. So the wavelength of the longest line, first line of the Lyman series is 1125 angstrom. With this, again I am to calculate the series limit, and I told series limit is the wavelength of the last line, shortest line ant kariteve. So N1 is 1. What should happen to N2? Infinity. For series limit or wavelength of the shortest line, N2 is infinity. Therefore again, 1 by lambda is R. So this is 1 by 1 square. So again, equation 1 divided by equation 3, lambda turns to be 911 angstroms. See again, just continuation, step-by-step calculation. We go on getting the results. The next one, students. Similar problem I have worked out in the previous session, where the problem says an electron transition occurs from n equals 4 to n equals 2 energy level in the hydrogen atom. So, an electron is jumping from the 4th orbit to the 2nd orbit of the hydrogen atom. Find the wavelength of the emitted radiation. Wavelength of the emitted radiation if the energy of the electron in the ground state is minus 13.6 electron volt. The problem says an electron transmission occurs from the fourth state to the nth state. So, electron is jumping from the fourth orbit to the second orbit. So, generally, E is minus 13.6 n square, so many times electron volt. We have studied in the theory energy of the electron in the nth orbit of hydrogen atom is minus 13.6 divided by n square. So here transition is occurring from E4 13.6 4 square, so many electron volts. Simplification is an assignment for you here. To E2, which is again minus 13.6 divided by 2 square electron volts. So what is the total energy liberated? So E equals E4 minus E2. Simplify. So E is so many electron volts. I have to calculate the wavelength now. So E hc by lambda is E4 minus E2. So lambda has to be calculated. It will be so many angstrom. Remember, you are converting electron volts to joule. 1.6 into 10 power minus 19 coulomb. Next one, students. Simple one. It's for y'all. Calculate the radius of second orbit of the electron in the hydrogen atom. I have to calculate the radius of the second orbit of the electron in the hydrogen atom. So what is the expression for radius, students? R is equal to n square h square epsilon naught pi m z e square. I'll give you the values of all the constants. You will be simplifying them. So n is 2, second orbit. Planck's constant h 6.625 into 10 power minus 34 joule second. Epsilon naught 8.854 into 10 power minus 12 farad per meter. Mass of the electron into 10 power minus 31 kgs. Z for hydrogen is 1. Charge of the electron 1.602 minus 19 coulomb. So using all this data, simplify and you will find the radius of the second orbit of the hydrogen atom. So this session, we have worked out problems again appeared from the previous question papers. The next session, I'll come up with few quantitative problems and few others from the paper from this chapter. Until then, have a nice time. Thank you.